Hello everyone. Today we'll be studying a topic from the chapter Solutions, which is the chapter number 2 in your NCERT textbook of grade 12. So we'll be talking about Rolle's Law from the chapter Solutions. But before studying Rolle's Law, let us talk about the basics of on what the Rolle's Law is actually based on. It talks about vapor pressure of a solvent and a solution. So let us first define what vapor pressure is, and then later on we can talk about Rolle's law and its equations, and we can solve some questions on them which has been asked in previous years competitive exams. Okay, so let us understand what vapor pressure actually means. So when I talk about vapor pressure, let us just consider that we have a beaker over here. Okay, and this beaker is then closed with a lid. Okay, now let us consider a solvent A in this beaker. There is some solvent A. Okay, now any solvent that we have will always be producing some vapors, be it water, be it acetone, be it ethyl alcohol, be it ethyl acetate. Any solvent that I take in the beaker, it is going to produce vapor. Now, since this beaker is closed, the vapor that will be formed only in this blank area or in this space that I can see over here. So what will happen as the time passes, the vapors will start being forming in this blank space. Okay, there will be vapors in this place. After some time, the air above the solvent will be completely saturated with vapors. What do I mean to say? That this air which is there present above the solvent, it has a capacity to take vapors, and at some point of time, all the capacity of the air to accept these vapors will be completed. The air will be completely saturated with these vapors. So at that time, we say that this vapor and this solvent are completely in equilibrium with each other. Okay. Now, these vapors that are in equilibrium with the liquid solvent will be exerting some pressure on the solvent. They will be exerting some pressure on the solvent, and this pressure that is exerted by the vapor of the solvent on the solvent at equilibrium is nothing but vapor pressure. I hope you understood. Just repeating it really very fast. We have a solvent, and this solvent is going to produce vapors. Okay, any solvent that we take, water, ethyl acetate, methanol, ethyl alcohol, any solvent that we take, it is going to produce some vapors. And since the beaker is now closed with a lid, the vapors will be getting a very little amount of space to occupy. Okay, so this air that is present above the liquid or above the solvent will be saturated with vapors, and that point we will say that the vapors and the solvent are at equilibrium with each other. Now, these vapors will be exerting a pressure on this solvent, and that pressure is called as vapor pressure. So, I hope this is understood. So, we'll just read the statement. The pressure exerted by the vapor molecules of a liquid when they are in equilibrium with the liquid, and that could be at a particular temperature, that is called as the vapor pressure of that temperature. I hope this concept is understood. Now we have understood what vapor pressure is. Next, we'll understand on what factors does this vapor pressure depend. Okay, so now the vapor pressure depends on two things. First is the nature of the liquid, what the nature of the liquid is, and second, it will depend upon temperature. Let us talk about each one in detail. First, let me talk about the nature of the liquid. So when I talk about the nature of the liquid can be of two types. Okay, then we can have volatile liquids, and we can have non-volatile liquids. We have volatile liquids and we have non-volatile liquids. Now, let us understand what do I mean by volatile liquid and not what do I mean by a non-volatile liquid. Okay, so when I talk about a volatile liquid, the only example or the very example that I get in my mind is that of a nail paint remover. Almost all of us has some point of the time used a nail paint remover. At least girls have used it. Okay, so what do I mean by a nail paint remover? A nail paint remover is nothing but acetone. Okay, so when I'm talking about acetone, it is a volatile solvent. What do I mean by a volatile solvent? Some liquids are going to boil at a very low temperature. Okay, they are going to evaporate at a very low temperatures. So this such liquids are called as volatile liquids. Okay, there are some liquids which will not boil at low temperatures. They will require higher temperatures to boil, and those liquids are called as non-volatile liquids. So very simple, what are volatile liquids? Those liquids which are going to boil at a very low temperatures, which are going to evaporate at low temperatures. Let's say for acetone or maybe ethyl alcohol, we have used sanitizers. So in sanitizers contains alcohol, and as soon as we rub our hands with sanitizer, the sanitizers evaporates off. Only the effect remains. So what is it? It is because the liquid over there, the alcohol over there is basically boiling at a very low temperature, and that is why it evaporates off very easily. Such liquids are called as volatile liquids, and the liquids which do not boil easily at a low temperatures, we require higher temperatures for boiling the liquids. Such liquids are called as non-volatile liquids. Okay, so I hope that is understand volatile liquid is acetone. When I talk about non-volatile liquid can be, let's say for example, it can be THF, okay, tetrahydrofuran, or let's say DMSO, dimethyl sulfoxide. Okay, so these all liquids are example of non-volatile liquids. Okay, now let us come to the topic of how does temperature depend, how does vapor pressure depends on temperature. So it's very easy. If I increase the temperature, of course, on increasing the temperature, we know that the solution or the liquid will start boiling, and if the liquid will start boiling, it is going to form vapors. So more vapors will be formed, and if more vapors are formed, basically the vapor pressure is going to be high. So if I increase the temperature, the vapor pressure is going to increase, or it is going to be high. And similarly, when I decrease the temperature, if I decrease the temperature, then of course it will take literally very much time to form the vapors, and then accordingly vapor pressure will be very less because the vapors will be less. So if we decrease the temperature, the vapor pressure will be low. So these are the two factors on which the vapor pressure is based. One is nature of the liquid, which will be depending whether the liquid is a volatile liquid or a non-volatile liquid. Volatile liquid will evaporate very easily. So I can say the vapor pressure over there, since they are evaporating very easily, the vapor pressure of over there will be more as compared to non-volatile liquids. And similarly with temperature, as we increase the temperature, the number of vapors formed will increase. And if the number of vapors formed is increased, so we can say there will be high vapor pressure. So that is how it depends. Vapor pressure depends on these two factors. Let us just see the slide. Okay, so volatile liquids and non-volatile liquids, liquids having weaker intermolecular attraction. So now the question comes, why is it so that some liquids will evaporate easily or at low temperatures, and why some liquids will evaporate at a higher temperature? So it's basically if when we talk about volatile liquids, the intermolecular attraction or the force of attraction between two molecules is going to be less. Since the intermolecular attraction between two molecules is going to be less, internuclear forces between them is going to be less. That is why it will be easy for them to evaporate from the surface. Okay, but when I'm talking about non-volatile liquids, in non-volatile liquids, the intermolecular force of attraction between two molecules is going to be more. The intermolecular force of attraction is going to be more. Since intermolecular force of attraction between the two molecules is going to be more, it will be difficult for them to escape from the surface, and that is why non-volatile liquids do not evaporate easily. So that is what they have mentioned over here. Liquids that have weaker intermolecular attraction, the ones which have weaker molecular attraction will of course be having higher vapor pressures because more vapors will be formed. Since more vapors will be formed, the pressure exerted by the vapors will be more. And similarly, the ones which have strong intermolecular forces of attraction, they have also given an example of the only metal in the liquid state, and that is mercury. Okay, so mercury basically is a non-volatile liquid. Though it is a metal, it is a liquid. So yeah, no, these are non-volatile liquids which will have very less vapor pressure. Okay, and then of course I've told you with temperature, vapor pressure and temperature. If you increase the temperature, vapor pressure is going to increase exponentially. What do I mean by exponentially? If you increase the temperature by 1 degree, the vapor pressure is going to increase 10 times. That it means by exponentially. I hope this is understood. So what we have learned till now is the definition of vapor pressure, what vapor pressure is, and the two factors on which vapor pressure will depend, and that is nature of the liquid, whether the liquid is a volatile liquid or a non-volatile liquid, and how does temperature or how does vapor pressure vary with temperature. So that we have already studied. Now, this was when we were considering about pure liquids. Now, we just when I talk about pure liquids, what do I mean by pure liquid? In the beaker, that when I was explaining you about vapor pressure, I had only considered a pure liquid A. So there was only A, there was only acetone, or there was only water, or there was only ethyl alcohol. I have not mixed any two liquids. So now we will be talking, what if I mix two volatile liquids? Okay, so now that is what we are going to talk about, the vapor pressure of liquid-liquid solution. What do I mean by liquid-liquid solution? I am taking over here two liquids. Okay, two liquids, both the liquids are going to be volatile in nature. What do I mean by volatile in nature? Both of them are going to form vapors, or both of them are going to evaporate at lower temperatures only. So, what are we going to study over here? The thing is, let us just assume over here. Again, I'll be taking a beaker, okay, and I'll be covering it with the lid. Now, here instead of just taking a pure liquid A, I will be taking two liquids. Okay, let us see. I have volatile liquid A and I have volatile liquid B. Okay, so there is A, volatile liquid A and volatile liquid B. Of course, since both the liquids are volatile, the vapors formed over here will be from A and will be from B. So A will also have some liquids and B will also have some vapors form over here. So basically, the total vapor pressure that this solution will be experiencing will be because of the vapors of A and the vapors of B. I repeat my statement, the total vapor pressure that will be generated or that will be experienced by the solution will be because of both the vapor pressure of A and vapor pressure of B. So now when I say vapor pressure of A and vapor pressure of B, instead of saying vapor pressure of A and vapor pressure of B, I will say partially it will be from A, partially the pressure will be from A and partially the vapor pressure will be from B. So now let's say PA, that will be the partial vapor pressure of A, partial vapor pressure of A. This will be partial vapor pressure of A, and PB will be partial vapor pressure of B. I hope that is understood. Why am I call it partial? Because half of the pressure, not let's not use the word half. Some of the pressure that will be exerted, that will be the total vapor pressure, will be some, so partially it will be from A and partially it is going to be from B. So that is why I call PA is equals to partial vapor pressure of A and PB will be equals to partial vapor pressure of B. Now the second question that will be arising, that it will be, how much vapor pressure will A be generating and how much vapor pressure will B be generating. So let us say if I talk about total vapor pressure will be equals to partial vapor pressure of A plus partial vapor pressure of B. Now I need to know what is the vapor pressure exerted by A and what is the vapor pressure that is exerted by B. The exact value that I need to know about the vapor pressure exerted by A and vapor pressure exerted by B. So this explanation, or if we need to find out what is the exact vapor pressure exerted by A and B, that explanation was given by Rolle's law. Okay, so now let us talk about Rolle's law, what Rolle's law had to say about it. So when I talk about Rolle's law, okay, so when I'll be talking about Rolle's law states that partial vapor pressure of A. Now we have already spoken about partial vapor pressure of A, that is PA, that is the vapor pressure exerted by A in a solution, which will be directly proportional to its mole fraction, that is XA. Okay, so whatever vapor pressure that A will be exerting will depend upon the mole fraction of A. What do I mean by mole fraction of A? The amount of A that will be present. Basically, it is an expressing, it's a term that is used to express concentration. So whatever A is there, whatever is the mole fraction of A, it will depend upon the mole fraction of A, how much vapor pressure is the A, if is A going to generate. Similarly, what is the vapor pressure of B? Vapor pressure of B will be directly proportional to the mole fraction of B. That is what Rolle's law have to say. So now if we understand what is the statement, let us read the statement. Rolle's law states that for a solution of volatile liquids, what do I mean by a solution of volatile liquids? I have taken two liquids A and B and both are volatile. The partial vapor pressure of each component, the partial vapor pressure of A or the vapor pressure that is exerted by A and the vapor pressure that is exerted by B will be directly proportional to their mole fraction, whatever the amount or whatever is the concentration of A and B that is present in the solution. Okay, so now if I have to solve this, we came to know that if we remove the proportionality sign, the partial vapor pressure of A will be equals to the product of pure vapor pressure of A into its mole fraction, and for B, it came out to be partial vapor pressure of B will be equals to vapor pressure of B in its pure state or in its liquid state into mole fraction of B. Now, what do I mean by PA naught and what do I mean by PB naught? This basically means vapor pressure of A of pure A. Vapor pressure of pure A. What do I mean by vapor pressure of pure A? Only when A was taken in the beaker, not B. Okay. Similarly, if I talk about PB naught, it is going to be vapor pressure of B. That is only when B was taken in the beaker. That is pure A, pure A and pure B. There was no any other volatile liquid or any non-volatile liquid. No, nothing. Just pure A and pure B. That time there was some vapor pressure generated by the liquid, and that is PA naught and PB naught. So this is what Rolle's law has to say. We will of course solve and get the equation for this in the next slide. I hope this is understood. Till now we have understood what is vapor pressure, what are the factors affecting vapor pressure, and what is Rolle's law. Rolle's law states that whenever we have a solution that is made up of two volatile components, there will be vapor pressure of A, there will be vapor pressure of B, and the pressure exerted by A will be called as partial vapor pressure of A, and it will be directly proportional to its mole fraction, to the mole fraction of A. And similarly, when I want to talk about partial vapor pressure of B, it will be directly proportional to the mole fraction of B. Now let us see how do we solve it and get an equation. Okay. So now let us just read, let us consider a mixture of completely miscible volatile liquids, and that is what we have been considering till now. We have two liquids A and B, and we have mole fraction, and the mole fraction is XA and XB. So their partial vapor pressure is going to be PA and PB, and PA naught, that is will be in their pure state, and PB naught will be in the pure state of B. So already we have got the equation from Rolle's law, and from Rolle's law the equation is PA will be equals to PA naught into XA. That is what we got. Let's say this is equation 1. And for PB, we got it as PB naught into XB. Let us say this is equation 2. Okay, and we already know that the total vapor pressure that will be generated for the solution will be equals to partial vapor pressure of A and partial vapor pressure of B. Okay, I'll substitute equation 1 and equation 2 in the equation of total vapor pressure, and that is going to be PA naught into XA plus PB naught into XB. Okay, this is going to be total vapor pressure. Now, since we are considering a binary mixture, now what do I mean by binary mixture? There are only two components that are making the solution, that is component A and component B. And already in our lower grades, that is in grade 11, we have studied that whenever there is a binary mixture, the mole fraction of the sum of the mole fraction of both the mixture of both the components is going to be 1. That is what we have already studied. So let's say even if you have three components A, B, and C, so the mole fraction of A plus the mole fraction of B plus the mole fraction of C is always going to be 1. So how many of the components you have got when you add their mole fractions? The answer is always going to be 1. Since over here we have considered only binary mixture, that is the solution is made up of two components A and B, the sum of the mole fractions is going to be 1. Okay, so now if I take the value, I can put it XA will be equals to 1 minus XB. Of course, you can do the other way around also. You can find it for XB also. Now, let us say this equation is equation number 3 and this equation is equation number 4. I will substitute equation 4 in equation 3. Then I'll get the equation as PT is equals to PA naught. I got the value of XA, that is 1 minus XB plus PB naught into XB. I'll solve this equation, and this equation I'll just open the brackets, PA naught minus PA naught into XB plus PB naught into XB. Okay, now here what I can do is I can take xb common from these two terms. So the equation will be equals to pt is equals to pa naught. Okay, here since this term is positive, I'll take it minus pa naught minus pb naught and bracket my xb. Okay, so this is the equation that we get for Rolle's law. Okay, this is a total equation that we can solve and we get for Rolle's law. Of course, you can also substitute the equation for I have found out the value of xa. You can find out the value of xb and you can do the other way around. Depends upon what the conditions are given in the question and what are the other factors or other things that are given to you in the question. I hope this is clearly understood to everyone. Let us see the conclusions that we get from the equation. So total vapor pressure over the solution can be related to the mole fraction of any one component. So when I go to the equation back, I see this equation, there is only one mole fraction that is required. That is, here we require xb. So even if the mole fraction of any one component is given to you, you can easily find out the total vapor pressure. Okay, so the total vapor pressure over the solution varies linearly with the mole fraction of component 2. So what does it mean by linearly? See, because over here we have taken this as 2, component 2, xb will be component 2, we can make an equation which forms linearly. Linearly means it is not going to increase exponentially, it is going to increase linearly. For example, if I increase the value of xb, the total vapor pressure with xb is going to increase. That is what it has to say. And depending on the vapor pressures of pure components 1 and 2, total vapor pressure over the solution decreases or increases with the increase of mole fraction of component 1. So it basically means if you increase one component, if you increase the mole fraction of one component, and accordingly the vapor pressure that will be formed will depend upon the more. For example, if you have taken A more, then the vapor pressure that will be generated above the solution will have vapor pressure of A more than B. So it basically depends on the mole fraction, how much quantity of a substance that you have taken, component you have taken, A or B. So if you see the graph over here, see this graph is very simple, though it turns out to be very difficult, but the graph is very simple. What we have taken over here is, let's say this point over here, this point over here represents the pure liquid A. So if I say pure liquid A, it means the mole fraction of A is going to be 1 and the mole fraction of B is going to be 0 because there is no B over here. Since it is pure liquid A, it has to be xa is equals to 1. There is no B, so value of B is 0. As in when I move from xa from this point to this point over here, it means that I am decreasing the component A, the concentration of component A, and I'm increasing the concentration of component B, such as up to this point, there is no A and there is only pure liquid B. Okay, so basically these 2 points signifies pure liquid A and pure liquid B. Now, since this point signifies pure liquid A, here the vapor pressure will be of pure liquid A, that is Pa naught. Pa naught is nothing but pure vapor pressure of pure liquid A. And this point signifies pure liquid B, so the vapor pressure over here will be of vapor pressure of pure liquid B. Okay, now what does it state? For example, when I'm moving from left to right, the mole fraction of A is decreasing. Since the mole fraction of A is decreasing, the vapor pressure that is generated because of A is going to decrease. And eventually, when it comes to this point, there will be no A, and since if there is no A, then the vapor pressure that is generated because of A will become 0. Similarly, when I'm moving from right to left, the mole fraction of B is decreasing. So if I say if the mole fraction of B is decreasing, then the partial vapor pressure that is generated because of B is going to decrease. And eventually, when there will be no B, the value will turn out to be 0. Okay, so here this line is going to give us the partial vapor pressure generated by B, and this line is going to give us a partial vapor pressure generated by A. And when I talk about this line will be giving us the total vapor pressure. So for example, if I'm asked what is the total vapor pressure at this point, so basically I will be seeing I can just extrapolate the graph downwards. Okay, and see what is the mole fraction of A over here and what is the mole fraction of B over here. I should know what is the vapor pressure of pure liquid A. I should know what is the vapor pressure of pure liquid B, and simply I can solve and get the answer of total vapor pressure of A. So that is what Rolle's law is all about. So this was Rolle's law. Of course, there are deviations from Rolle's law. We are also going to study that deviations. But before that, I need to explain something about the vapor phase. Okay. See, now when we were talking about mole fraction, okay, when we were talking about mole fraction, we completely stated that this mole fraction is there in the liquid. For example, we had taken XA and we had taken XB. So XA and XB will basically tell me how much amount of A and how much amount of B is basically present in the liquid phase. How much A we have taken and how much B we have taken. Also, this PA and PB will tell me what is the vapor pressure, or let's say now the partial vapor pressure of A and B. What do I mean by partial vapor pressure of A and B? So if in a solution A and B is taken, what is the vapor pressure that is generated by A and what is the vapor pressure that is generated by B? Now the question comes, we have understood what is the pressure that is generated by A and what is the vapor pressure that is generated by B. That is already given by Rolle's law. But the question is, what is the composition of A in the vapor and what is the composition of B in the vapor? Basically, we need to understand how much of vapor of A is present and how much of vapor of B is present. So for that, for the composition of A and B in the vapor phase, we use the letters YA and YB. Okay, so Y and YB are basically going to be the mole fractions of A and B, but it is going to be in the vapor phase. Okay, and the formula for that is partial vapor pressure of A is equals to YA into P total. So I can also write it as YA is going to be partial vapor pressure of A upon total vapor pressure. Similarly, for YB, I'm going to write as partial vapor pressure of B upon B total. Okay, we can also solve this because now we know what Rolle's law is. PA will be equals to PA naught into XA upon, we can also write for total vapor pressure, that is PA naught into XA plus PB naught into XB. Similarly, here also for YB, we can also solve and write PB naught into XB upon PA naught into XA plus PB naught into XB. I hope this is understood. Okay. So in the next part of this lecture, we'll be solving some questions.